average rate of change of a function. Okay, so let's take a look at a function. This is f of x. And let's say I have 2 points. So this point is point P, and this is point Q. And the coordinates of P, x1, comma, and you'll tell me what, and coordinates of Q, x2, comma. What do you think is the y coordinate if the point is on the graph of the function and its x coordinate is x1? What will be the y coordinate?
y1.
You could say y1, yes. In another way, is there another way? y1 is perfect. I completely agree. y1 is perfect. But is there another way? And this is very important. So the points, both points are on the function.
So 0?
The x coordinate is x1. How do I determine the y coordinate? No, it's not 0. So one option is to write y1 and here to write y2. But there is another option, and I want the second option. If a point is on the graph and its x coordinate is given to us, how do we find the y coordinate? So let's go back. We looked at this problem. 28 on page 11. We were given the function, so we have the function. We were told, find the value of the function when x or t is 13. Find the value of the function when t is 30. What did we do to find that? I want the same thing here.
Do you mean f of x?
Very good. F of x1 and f of x2. Not of x, but of this specific value. Excellent. Okay, so now we want to find the average rate of change of this function between x1 and x2 on the interval, closed interval, x1, comma, x2. What this represents is basically the slope of this line. That's it. That's what it is. It's the slope of the line PQ. Can anyone give us the slope of the line PQ? Ready. Anyone?
I don't know if I remember correctly, but is that y2 minus y1?
This is the y2, so f of x2
yes.
minus, indeed, excellent, over x2 minus x1. Good. So if this is the distance function, and I start in Baltimore, and I go to New York, and after I come back, you ask me, okay, you started in Baltimore and you went to New York. What was your average speed? I'll say, okay, it took me 6 hours. So it's 200 miles divided by 6 hours. My average rate was blah, blah, blah. However, when I'm in the middle of my trip and you call me and you say, tell me what your odometer says at that instant. Okay, so if I have this function from P to Q, I find the average rate of the speed, right? In other words, the average speed on that interval. But if you call me and you say, tell me, so this will be that the slope of this line, PQ. But if you call me when I pass by Wilmington, Delaware, let's say here, this is Wilmington, and you say to me, tell me what your odometer says, what is your speed at that instant, you're really asking me to determine or give you the slope of the tangent line. So this is called a secant line. It crosses the graph of a function in at least 2 points. And the slope of this line gives us the average rate of change between these 2 points. But this is the tangent line. This one will give the slope of this. Slope is average rate. For this one, its slope is instantaneous rate of change. So please keep this concept in mind, because this is what we're going to do in chapter 1. So the slope of this gives us the average rate of change between these 2 points. The slope of the tangent, however, is the instantaneous speed or instantaneous rate of change at that moment. Okay, good. So where am I getting now? Where is my target? My target is something called, and I'm going to move on to the next page, something called the difference quotient. But I needed this for you to understand what's happening, and then we're going to talk about the difference quotient. They are extremely related, and you'll see how in a moment. Same graph. Same 2 points. P, this time, is of x comma f of x. Q is right here. Very close. But I'm going to zoom in, because if I put Q here, nobody's going to understand anything I'm doing. So Q is very, very close, but I am going to zoom in. So Q will look very far away. However, Q is extremely close to P. So here's my Q. And just to make sure, this is X. And this is tiny. Small. Very small, because Q is here. We're going to call it or denote it by lowercase h. H is tiny. Okay, so this is X plus tiny. Can anyone please give us the coordinates of Q now? It's not different from before, just the notation is slightly different. Everything is the same. Can anyone give us the x coordinate of Q?
X2.
The x coordinate of Q.
X plus H.
That's it. There is no discussion there. And now, can anyone give us the y coordinate of Q?
X plus H.
That's it.
Okay.
Is this clear, everyone?
Yeah.
I will never be able to guess if you have a question. You have to speak up. Okay, so then, like before, I want to determine the slope of PQ. And the slope of PQ is the difference quotient. I like to denote it by DQ. That's it. Can anyone give us the same formula? Everything the same? Just the notation is slightly different. But the notation is very important for chapter 1.
Is it f of x minus f of x plus h over x minus x plus h?
Perfect. However, we are going, excellent. However, we are going to write it y2 minus y1 over x2 minus x1. But what you said is perfect anyway. y2 minus y1 over x2 minus x1. Exactly what we did 3 times. Good. Obviously, I'm going to simplify these two. I meant here. And that is our difference quotient. So let's analyze what it means. It's almost, because they are so close, it's almost the instantaneous rate of change, but not quite. So this is, so from now on we have to memorize this, or you have to put it in your notes forever. So f of x plus h minus f of x divided by h, and we're going to say so that this is almost, not exactly, not quite, the instantaneous because they are so close, h is tiny, instantaneous rate of change of a function. Okay, almost. You'll see what happens next. So in other words, what I'm saying is when q is very, very, very close here, this is almost this because q is here. So it's almost the slope of the tangent line at that point. Okay, now one remark, and we're going to choose a function and determine its difference quotient. You choose, of course. So here's what I would like to mention. Rate of change. Rates of change have 2 measurement units. One for the top, one for the bottom. Okay? One for top, one for denominator. Okay? So if you ask me, what is your rate of change? I'm not going to say 60 miles. I'm going to say 60 miles per hour. So please keep that in mind. All rates of change have 2 measurement units. One coming from the function, the y variable, and one coming from the x variable. Okay, and now let's open on, I think it's 20-something, 22. So I'm going to share my screen. Okay. I can see. Where is my rate of change? So these are the answers to quick checks. I will definitely work on those immediately after class, after you review what we did in class. Okay, where are my, okay, so for this function, I don't care to graph it right now. We're going to graph a lot. I just want you to choose or create a quadratic function, for example, and let's determine its difference quotient. Give me any quadratic function you want to work on. So let's start with the quadratic function. Find and simplify the difference quotient for f of x equals. Make one up. Anything you want. Anyone?